Today we will be discussing more or less normal diffusion processes. So we are in the realm of Gaussian central limit theorem, no power laws. And I'm going to go back roughly to 1905 and to the work of Langevin and Einstein that described the motion of a Brownian particle. So the observation of Brownian motion was already in the 19th century, but now we want to build a physical theory of Brownian motion. So you all know that Brownian motion is something roughly like this. You have a particle in a medium. The medium, if you want to think about it, let's say it's water, but it can be many things. And you have a small particle, let's say roughly of a size of a micron, and the trajectory in space of this particle is very random, and it does something like a random walk. And indeed, you can model this as a random walker in space, making random jumps up, down, left, right. You know that this is described by the diffusion equation in the long time limit. The displacement of this guy is going to be Gaussian. This is all known. But what we want to do here is slightly different. First of all, the first question we're going to ask is, what is the description of the velocity of the particle? So in physics, we always start with the velocity. We have a phase space in Newtonian mechanics. We have a velocity, and we have the position of the particle. Surely this particle has some velocities. And how are these velocities? How will we describe them? In the measurement that we were talking up to today, we simply ignore the velocity. We're just looking at such times that we sampled this trajectory after some long times, and then we didn't care what was the velocity. So you don't always care what is the velocity. You don't need to measure the velocity, but if you want to, you can. And to understand the physics, you need to know how is the velocity changing in time. So how will you build such a theory? Well, first of all, let's guess what's going on. You have the velocity as a function of time. So what is going on? What is the velocity as a function of time? You think a little bit. Okay, let's say at time t0, you start with some velocity v0. So v0 is the initial condition of the velocity. So, well, I mean, this particle is in a very complicated medium. The temperature of the system is T. The mass of the particle is capital M. This is what you know. This system also has some general properties like the viscosity of the system, of the medium itself, of the water surrounding the particle. What is V of T then? Well, in this medium, of course, you have many atoms, many molecules. It's very difficult to calculate this velocity. No one knows how to do it, and no one can. And it's not only a matter of no one can, even a computer cannot. I mean, a computer you can follow this type of velocity by solving the Newton's equation, but let's say for a few picoseconds, and no one cares about these timescales. The biggest computers cannot solve this problem yet. Maybe another 10 years or so, they'll be able to go from 10 picoseconds maybe to a nanosecond or something. And even in this nanosecond, they don't know what are the forces, so it's all an approximation. No one can calculate exactly the velocity, but it's not even worth the while. Why is it not worthwhile? Because from a mechanical point of view, this velocity of this particle is related to the velocity and the initial condition of all the other particles in the system. And you don't know them anyway, because you should know to solve this, like in Newtonian dynamics, you need to know, first of all the forces in this system, no one knows. Secondly, what are the initial conditions of all the particles, no one knows. And anyway, this will, after a few picoseconds, this will be totally irrelevant, because then if you get some hit here, so from something from outside, it will change the initial conditions. So it's a totally hopeless problem to solve it, like in Newtonian mechanics, and even today's computers help us a little bit, but only for very short picoseconds or very short time scales, so they are not really useful because of this huge complexity of the problem. But we can think for a change, and then what is the velocity? Well, we think in a stochastic way. This is not a microscopical theory. So, okay, we start with some velocity, and then what will happen to the velocity? It will be something like this. It will look and then you go to infinity. So, of course, this random trajectory, random path of the velocity is a random function. That's why I said we cannot calculate it. And when you repeat the experiment again with the same initial condition of the big particle, of the massive particle, you can start here again. You just put the particle, you give it some velocity, and it will behave. But of course, this path is totally random and not reproducible. So we need to look at the statistics of this path. Now we think, what do we know? Okay, we know the initial condition, but we also know something on the long time limit, and that's really marvelous. So in the very long time limit, so what is happening first of all? At the beginning, you lose your initial velocity, and then you go into something which is fluctuating, but it is a steady state. We'll soon discuss what happens in this first part of the system. We want to know what is this time scale. After how long do we lose the memory of the initial condition? That's question number one. But we know something very powerful on the long time limit. What do we know in the long time limit? So what do we know here? What is the velocity distribution? So there's some velocity distribution. Our ultimate goal is to find, in principle it will be in 3 dimensions, but I'll do it in 1 dimension, the probability density of the velocity of the particle at time t. This is a normalized distribution. The initial condition is a delta function on this initial velocity. But what is this PV of t in the very long time limit? What is it? It's easy, you know it. What is it? Good morning, everyone. You have a temperature T. So in the limit of long time, T to infinity, this has to be the Maxwellian distribution. So in the limit of long time, the velocity distribution here, what do I mean velocity distribution? I start with many particles with initial condition, and then I look at it here, and then you'll have here the Maxwell's velocity distribution of the particle with mass m, independent of the medium, which is of course a miracle, but it also happens automatically due to equilibrium statistical physics. Because to remind you, in equilibrium statistical physics, no matter what is the Hamiltonian, you write the Hamiltonian of the whole world, if you want, it's equal, it has a term there which is p squared over 2m of the big particle divided by k Boltzmann t. So when you trace out, when you remove all the other degrees of freedom of both position of this particle and all the other particles, the velocity distribution of this single particle, magic, is given by something universal. Why is it magic? Okay, you got used to it, so you're not so excited, but I'm still excited because it depends only on T, the temperature, and the mass, of course, because kinetic energy depends on mass, but it doesn't care at all what is the medium. You put it in honey, you put it in water, you put it in whatever you want, only temperature is important. So we know the velocity distribution. So down here, this is the velocity distribution. It is given by Maxwell. Maxwell distribution is, of course, a Gaussian. You know this, I hope. And you know here the variance of the velocity. So what is the variance of the velocity? V squared is equal k Boltzmann t divided by m. That is the equipartition. Equipartition tells you that the potential energy, the kinetic energy, mv squared over 2 is k Boltzmann t over 2. And you know this very well. This is a well-known equation. So this is the velocity of the massive particle in the limit of very long times. Okay, great. So I know 2 two things about this function. I know two things. I know how it starts with the delta function on V0, and I know how it ends. It has to go to a Gaussian. And you'll see later more and more that we always look, in usual Newtonian mechanics, also in quantum mechanics, you usually, what you do is you have an initial condition, and you solve some equation, and you propagate, and then you know what's the future, which is very natural because we want to know what's the future. But in this type of series, you, of course, should know the initial condition, but you also know what is the final condition when the system is in thermal equilibrium. So you assume thermal equilibrium. So you know where you start. You are born. You know where you end. When you die, you are in equilibrium. And this fact that you know the future, because you assume that the thermal equilibrium, the older theory, the thermal equilibrium theory, Maxwell-Boltzmann-Gibbs theory, is valid, you know the future. And because of that, you will see that beautiful things happen. And these are related to something called the Einstein relations. That is something Einstein understood, that because you know the final stage, you can say something on the whole dynamics all along. And that's actually the main part of the theory, using this equilibration to say something clever on the history. Now, we have to think a little bit what happens at the beginning, without doing equations, of course. I mean, later we'll do equations. So just to write it down, the P equilibrium of V, so P equilibrium of V, by that I mean in the long time limit, so it's independent of T, is just given by the Maxwellian, which is specifically with all the 2 pi's, 2 pi k Boltzmann T to the power half, m to the half, exponential minus mv squared over 2 k Boltzmann 2. And this is simply, you see this is very simple, this part. This is simply the kinetic energy of the particle, mv squared over 2. We are assuming here many things, of course, already now. I think it's clear, but I'll still state them. I assume that this particle, there is no external field that is driving the particle in one direction. So I can apply, let's say, an electric field. I can put a charge on this big molecule, and it can move in one direction. So I assume on average there's no forces here, external forces, and that's why eventually there's no average drift velocity. Later we will add a force. That will be a different story. But for now there's no external forces, and on average the bath is all the liquid around it is not pushing the particle in any particular one direction. That's why in the long time limit, I didn't mention this, but because it's obvious, the V average of the massive particle is 0. And that's why, on average, it's going to, this is 0. This line is 0. And you have some fluctuations around it, and we know the variance. OK, so now we want to say something about the initial condition. What else do we know about this particle? Well, from courses, not stochastic courses, but from just physics. So we know, because you did this experiment in high school or whatever, that if you take a particle in a medium, let's say with a force, and you drop it, it will reach a finite velocity. And this is because you have a drag, you have a friction. The friction is described by something called the Stokes law from hydrodynamics. What is it, but what is actually hydrodynamics when you think about it? What is the, I mean, hydrodynamics will describe a particle in some fluid, and it will give you some rule on the velocity of the particle, which I'll soon remind you. That's Stokes' law. How does the average relax? But in hydrodynamics, it's of course a beautiful and very powerful theory, but you throw away the fluctuations. There's no thermal random fluctuations. Because in hydrodynamics, you consider a typical problem, a particle in a liquid, you have some boundary conditions, it's moving, and it has some velocity, but there's no noise like this random force. So the hydrodynamic laws tells you that the average of V minus gamma V. Actually, this you know even not from hydrodynamics, but just some common sense. So we interpret hydrodynamics and macroscopical theories by the fact that it is an ensemble average over many particles. So what does this law tell you? So it tells you that the average velocity as a function of time, the solution of this equation is obviously V. Let's say you start with some V, with some initial velocity, is a simple exponential decay. So you start with this initial velocity V0, then you decay to 0 on average. This is the macroscopical law, and you know it very well. I mean, you go to the beach, you are in the water, you push something, you give it a velocity, and after some time it stops. So that's the law. You give it some velocity V0 and it will stop. If there's no waves, it will completely stop, right? You just push it. You have a little rubber duck. You push it, whoops, and after some time it will stop because its velocity is decaying. The initial condition, how strong you push it, and then it will decay. And I'm telling you it will decay, according to hydrodynamics, it decays exponentially with some coefficient gamma. So going back, what is happening here? We say that the real velocity, there is an average behavior, which you can obtain by putting many Brownian particles and then averaging over many trajectories. This is the average. We want to go beyond the average. So this curve is simply the average. And beyond the average, you have some fluctuations around this line. Now, these are the fluctuations that I draw at the beginning. Now, the size of these fluctuations, let's say at the end, you see it's K Boltzmann T over M. If you have here 1 kilogram, this thing is practically very small. So you don't see these fluctuations. It's difficult to measure. But if you have a small particle, some molecule in the cell or whatever, then you see these fluctuations, or if your measurement device is good enough, you can see these fluctuations. So the macroscopical law is describing the average. Sometimes the fluctuations are important, small particles, thermal particles, small mass. Sometimes they are not. So, of course, this Stokes law, it's not that it's not valid. It's valid and it's very useful, but usually you apply it to relatively big particles, not micron size, such that you neglect the fluctuations. But when you go to the real world of smaller particles, you see these fluctuations, and we know exactly how big these fluctuations are here at equilibrium, and now we are adding on this relaxation law. This thing is called the relaxation law or dissipation law. We are adding this. Okay, so we'll soon construct a theory, but we know something else. If we know hydrodynamics, we know Stokes law, so we know something, and that is that gamma, this coefficient, what is it? You see, when we did random walk theory, we said, okay, you're going to jump left and right with some length of the lattice, some time between jumps. We don't have this because we don't have even a lattice, but we have all kinds of coefficients, gamma. So you see gamma as a unit of 1 over time. But gamma from hydrodynamics is given by 6 pi a eta over the mass. So A is the important parameter, is the radius of the particle. Eta is the viscosity. Viscosity of the of the medium. So this is a property not of the sphere, not of this particle, but all the medium outside, and this you can measure by shearing the whole system. And if you switch particle 1 with particle 2, let's say they have the same mass and the same size, you are not going to change this gamma. So the chemical compound, how this interacts with this system is not important. So it's physics, it's not chemistry. Actually, this is not trivial, because at least when this particle is big enough but small enough for the fluctuations, what is important is not the interaction on the surface, which is specific to material A and material B. Of course, the size is important. The size is a physical quantity, not a chemical quantity. But what is important is the viscosity of the medium. So you are done. You essentially know exactly what is this gamma. So the only thing we need to do now, we understand how the average is relaxing. We understand the fluctuations and long time limit. And now we want to build a stochastic theory for intermediate times to describe everything, including these fluctuations. So the goal is, as I said already, what is this PV of t, but not in the time t to infinity, but generally. And for that we construct an equation. And the equation is called, in general, this equation is called the fokker-planck equation. This very specific equation that I'm going to discuss has a name. It's called the Rayleigh equation, or it should be called the Rayleigh equation, but Rayleigh was forgotten, so this is an example of a fokker-planck equation. So these equations are very general. So we are applying them to a specific problem now and trying to understand. And we are doing this, what we'll do today, I'll first introduce this the way that is always introduced in physics, in a phenomenological way. What does it mean, phenomenological? I understand the physics, and then I write down the equation, and then later I try to justify it from a more macroscopical point of view. So the idea is, I look at this trajectory, and well, at least for me, this randomness is something like diffusion. So on one hand, the temperature, if the temperature would be infinite, your velocity, the variance here will be gigantic, and what will happen, you start here and then you spread out, and then you'll have like a diffusion in velocity space. So on one hand, we have something like diffusion. On the other hand, we have something that causes the particle to relax. And what is that thing? That is, of course, the dissipation. That is Stokes' law. So what we are going to do now is we're going to guess an equation that has in it those two elements. And later we will see how to make sense of this. So I write down, what I care about now is the change in time of the probability density function. So again, we know how this is at time t equals 0, and we know how this is at infinite time, and we want to know for everything. So we assume that we can write an equation for the time derivative of the probability density, like we had in the diffusion equation. Remember, diffusion equation, we have d over dt p, then it was of x, and t was equal diffusion times second derivative of x times p. So here we are looking for this type of similar equation, but now we'll have something else. Not only diffusion and velocity, but also some drift. Drift, I mean that something is causing it to relax to equilibrium, actually. So already here we are going to assume several things. One assumption, it will become clear later, that the paths are continuous. So this equation is an approximation, but it is a fantastic approximation for a Brownian path. So when I mean by paths are continuous is the following. I have v of t, and then I think of these paths as continuous in time. This is a yes, this is more or less continuous, but we could have another thing. The velocity is a constant, and then it jumps here, then it goes like that, then it goes like that. etc. This is a jump process. This is time. This is v. This is not the case. We will later see what it really means. It's not that you might have this, but this time between, you can think about this in the following. Think about a particle in a gas, a big particle in a gas, and once in a while it has a collision, and then this collision will change its velocity. We are assuming that in the liquid, the collisions are so frequent that you don't see these microscopical jumps. We'll come back to this jump process later, and we will show how it goes to this limit later on. So the collisions are very, very frequent, but very small. So you see here you have a jump in the velocity. This is a big change in velocity. We are assuming that the surrounding media is consisting of small atoms or molecules, such as each collision is very tiny. It just changed the velocity a little bit, and these collisions are so frequent because we have a big particle that the path is continuous and you don't have suddenly a jump here or jump there. If you would, then you will have some other effects which are not described by a first order time derivative, but rather by integral equations. It's a totally different story. We also assume that there is no memory. And no memory means that when you change the velocity, or you change the probability density, this depends only on the state of the probability density at this time t and not the full history. The particle doesn't remember that a few days ago it had some history and then suddenly its velocity became very big. It forgot about it. So this is what is no memory means. We will again go to systems with memory later on in the course. And this is an approximation. Remember, now we are in 1905. So it means, mathematically, it means that the time derivatives we like, so we have this dB of dt, and we don't have some memory kernel, which would mean I will take some memory and I'll have to integrate PV of t on the whole history of the system. This is we are not doing this, and the reason is that each time you kind of collide with the particle, the system then in the surrounding quickly relaxes. So the molecules in the medium are colliding so fast that you don't influence them, and then you influence back. This is again an assumption that we had also in the diffusion equation. We assume all these type of things. So let us do that, and later on we will continue. And then the first thing, again, in a phenomenological way, is let's guess an equation, more or less. And then we have A d over dv v p v of t. This type of an equation is what I called before fokker-planck equation. And in this equation I have two unknowns, b and a. I want to find them. I want to say what they are. And I'm optimistic because I have two informations on the system. One is what is the average relaxation. So I have here gamma, which I don't see yet, but it has to be related to A and B. And I also have K Boltzmann T over M. So I have two parameters, gamma, that I can maybe relate to these two parameters A and B. That's what we're going to do now. Now, what did I do here? I said the following. You see this noisy part of this thing? This is described by some diffusion. But in addition, I add something that causes it to relax. And let us see why this is what I say is causing you to relax, okay? Relax means go to equilibrium. So this is kind of easy. The first thing we do is let us calculate the average of V. It's more correctly, how it changes with time. So this dot is the time derivative of V. That's easy to do. You just take the equation d over dt v p dot v of t dv. So you see what is the change of the velocity as a function of time. Here I'm integrating over v. It's this probability density function, how it changes in time. Again, this is simply this part, and then because I want the average, I need to integrate over all this thing. Of course, I don't know, at this stage I don't know what is p, but I'm going to write an equation for p, then I can solve it, etc. So this guy, on the other hand, is equal to integral from minus infinity to infinity b times v, the second derivative of v, p, v of t, dv. This is this first term, plus a v d over dv, v, p, v, and t, dv. I just added this v and v, here's this v, here's this v, and I plugged in the equation. Now, you see here by integration by parts, and using the fact that the probability density function of the velocity at plus infinity and minus infinity, when the velocity is very big, is 0, this guy, integration by parts, this gives you 0. Because I just do integration by parts, then I have the second derivative, one of the derivatives will go on the v, will cancel it, I'll have a minus sign, and then I'll have the derivative with respect to v of p, then I know how to do the integral, and then this is simply the probability density at plus and minus infinity, and that is equal to 0. This we of course know, because this is like the average. Think about v, imagine that a was 0 and here you add an x, then of course this would be like the position of a Brownian particle doing a simple following the diffusion equation. Then the average of x from symmetry is 0. I mean, this is pretty obvious. So I'm left only with this term, and this term I can do integration by parts. So also here I do integration by parts, and then when I take the derivative, this is going to cancel this velocity, but I have this velocity inside. This one, which is maybe strange for you. Why did I put here velocity v? Right? But let's see what happens, and then you will understand, I hope. Then I get that this is simply a times v. So then we know what's a. What is a? Here I have a minus from the integration by parts, so a is equal gamma. Now, of course, you could have asked me, wait, why did you put here v? Why didn't you put here something else, some function of v? Well, yeah, you can put here a function of v, but if you put here a function of v, then you'll get v dot equals a, the average of a function of v, right? But you know that the macroscopical, or you assume that the average is given by this law, so instead of a function of v, then you have to have a linear function of v. But in principle, if someone would tell you, something like, oh, you know, here the friction is not linear, maybe you have something else, and so maybe here you need a different function of v. But I'm talking about linear friction. What do I mean by linear friction? I mean that the velocity, I mean exactly this, that v dot is equal minus gamma v. This is what we call linear velocity, linear friction, where this gamma is independent of the velocity itself, right? Where this means, for example, that the velocity of the particle is never very, very big. For example, in the system you have sound waves. So this velocity has to be much smaller than this sound velocity. Otherwise, the friction itself will become nonlinear. For example, if you have a parachuter falling down from space, the velocity acting on this parachuter is not linear in v. Stokes' law has some domain of validity, but it will be actually quadratic, etc. There are many corrections to linear friction. So we are talking here on the situation where the velocities are, you start here not with some gigantic velocity and the speed of light, which will obviously ruin all the system and make something very crazy going on here. So the velocity is actually assumed always weak, but velocity can be, V0 can be much larger than k Boltzmann T over m, but still the friction is linear. So you can say this is an assumption, but fine, we are doing here a very phenomenological theory. So we know what is gamma. And now we want to know what is A. We know what's A, and now we need to know what's B. Okay, so let's find B. That's now going to be also pretty easy. What is B? That's, again, something like the diffusion constant, but in velocity space. But don't be confused. There is also space. There is also position. There is also velocity. We'll talk later about the position. So later we'll have to ask how this two coefficients is related to d. D is the diffusion constant of the MSD. Means x squared is equal to dt, right? The one that we used in this when we describe space and not velocity. So this will come later. So now we want to find B. So I already told you how to do it. We know the limit time to infinity, and we assume equilibrium. And what is equilibrium mathematically is the time derivative of the probability density function is 0. You assume that at very long times the distribution of the velocities is acquiring stationary state, and it's time independent, which means that the derivative of the density is 0. And in that case, this equation becomes very easy because the left-hand side is going to be 0. So we can add here equilibrium. And it's not only that, we know exactly what this equilibrium, this is the Maxwell distribution. So we have P, so we have all this is equal to 0. B, second derivative. Now I know already what is A, so I can write it down. A is gamma, this Stokes friction. And then I have to write here P equilibrium, which is a function of V only. And again, let us write down what is P equilibrium. It's Maxwell distribution. You have it, you don't need to write it, but I'll write it here. So you have the kinetic energy, 2k Boltzmann T. Here you have the normalization, 2 pi k Boltzmann T m to the power half. So we know this. And then what we need to do is we need to take the derivative, okay. This guy, we can make it, you see, you have the second derivative and you have the first derivative. So slightly better is to write this d over dv, b, no, not gamma, d over dv, this one, plus gamma v. The prefactor here, the normalization, is not important. Here we have mv squared over 2k Boltzmann T. Now, when I take the derivative, then I get this derivative. I get here d over dv minus b times m v, I'm taking the derivative in this Gaussian, divided by 2 k Boltzmann T plus gamma v. All this is going to be equal 0. This we take what's inside here as being 0. You cannot take it as a constant because it depends on v, of course. I mean, For any v, this is a solution, so v can be anything, so it has to be 0. And then we see what happens. We see that b m k Boltzmann t is equal gamma, or b is k Boltzmann t times gamma over m. Where I made a mistake. Yeah, I made a mistake. All the time I made a mistake, but it's not your fault. I want to define it here as over 2. This is over 2, this nothing happens here. Here over 2. This is over 2. And then I have another 2 here. These two cancel, but I'm adding by definition another 2, and then this is the correct result. You'll soon see why. I mean, it's just a matter of definition. I mean, b over 2 could be b, but this is the usual definition in textbooks when you have something over 2, because it's something to do with the definition of the diffusion constant in the usual case. This is x squared is 2 dt. This 2 you carry on along because of Fick, you want to define all this guy as d, but never mind. This is just definition physics. It's not important. What is important is we found this guy, and then we can just summarize. We have the equation. This is the final equation. This is the derivative with respect to t is gamma, because you see both b over 2 is proportional to gamma, and also a is gamma itself, so I can put gamma outside. And then here I'm changing the order, the derivative with respect to v plus k Boltzmann t divided by m, second derivative of v, pv, and t. I just write p. It's a function of v and t. You see that the friction comes as a global factor behind this equation. Why? Because the equilibrium, which is described here, k Boltzmann t over m, which is the Gaussian, is independent of gamma. That's the marvelous thing about equilibrium physics. It does not care what is gamma. Equilibrium is independent of gamma, so that's why here inside we don't have gamma, and then it's multiplying both terms. So what is it saying? If we define this as diffusion, and we define this as friction because this gives you the Stokes law, you see that gamma also influences the diffusion, because gamma times this guy, but it also defines the relaxation. We got here the Stokes law. So the friction is somehow entering in both. It's not that you can write one mechanism, this guy is not independent of the friction here. These two guys are related to one another. This is something called fluctuation dissipation. There is a relation between the fluctuation. What is the fluctuation? This is the fluctuation, and this is related to dissipation. There is a relation between them, and this is something very deep in physics, and this will lead us soon to the Einstein relations. So let us now briefly just look at this equation and then try and see what it tells us, okay? Let's solve this equation. I'm not going to solve it. I'm going to give you the solution. You'll solve it in homework, but just let us look at some properties of this equation. This fokker-planck equation, and what it says, does it make sense or not? So first of all, we can look at the average velocity, and that is equal v0 to gamma t. You just multiply this by v, you average, then you get only this term, and then you decay. Here, this is of course obvious because I put it in by hand already. So I used this already, so now I'm just checking it's not a real thing. Here I'm using the fact that pv t equals 0 is a delta function. On some velocity, the initial condition is v0. Slightly more useful is v squared average. How do I get v squared average? Well, I need to multiply. This is the trick. You can do it many ways, but you multiply by v squared, you integrate over all velocities, you get a time derivative of v squared average, which I'm going to write the solution, and then you have v squared, and you do integrations by parts. You get an equation for the second moment, and it's easy to show that this equation for the second moment is related to the first moment, and then you can solve it. I'm not going to do this. I'm just going to tell you what is the solution. And the solution is given by the following. v0 squared, that's of course the correct units, 2 gamma t. And this, you see, this term is simply this term squared. This is just the average velocity squared. This is how you would relax actually in a zero temperature. If you had no temperature, meaning no fluctuations, of course then the liquid will be solid, but that's a different issue. So all this would not be valid. But then you have k Boltzmann t over m, 1 minus exponential 2 gamma t. And then you see what you expect at short times. And now we understand one new thing, that what is the meaning of short times? Short times means gamma t, again, this is Stokes time scale. One of this is a Stokes time scale. Gamma t less than 1, then you have here v squared. That's the initial condition. So for example, if you have no friction at all, gamma is equal to 0, v squared is v0 squared. This is 1 minus 1, and forever you have the same velocity. That is Newton's limit. No friction whatsoever. Of course, that's not so interesting. On the other hand, and on the other limit, gamma t much bigger than 1, then you see this initial condition decayed in time. You forget where you started after some time. And then this is equal k Boltzmann t over m, which is this prefactor. Now, when we think about this, after a long time, let's say I start my measurement after the system is relaxed already. So my time is much bigger than this guy. Then my velocity will be random, of course, as a function of time. And you see, I kind of try to write, you see that there is a correlation. The velocity here and the velocity here are nearly the same. Why? Because you forget, you have friction, and then the time scale between when you lose your correlation is given by 1 over gamma. After time, which is 1 over gamma, then you already forgot, or it's much bigger than 1 over gamma. So you see, here I don't plot it up, down, like independent random variables. The two velocities nearby one another are correlated because you have friction. Of course, if you sample this trajectory, you just take a velocity here and a velocity there and a velocity there, and your measurement device can sample, but only rarely, on a time scale much bigger than 1 over gamma, then you don't see it at all. Then you'll say, the velocities are totally independent of another. So seeing this correlation, you need a measurement device who can see on the time scales less than 1 over gamma. That's very obvious. One way to describe this process is by looking at Vt plus tau times Vt, average. This object is called a correlation function. It's a velocity correlation function. You can do this actually when you think about it in two ways. One, let's say you have only one trajectory. What you do is you take your velocity path, if you are able to measure this, and you look at two time points, this time and this time. And the difference between these two guys is tau. Then you look at two other points in time. The difference is again tau. And then you take the velocity here times the velocity here, plus the velocity here times the velocity here, and you do it along the path. And then you add this up, and then you get what is called a time average velocity correlation function. The advantage here, you need only one trajectory. So I hope you understand what it means. If you don't understand, this is simply Vti plus tau, Vti, sum I equal 1 till n. I is a sampling time. So you sample your trajectory, and you divide by n. This is a time average. What I mean by that this velocity here is your path. On the other hand, you can do something very different, and you can generate in principle, but this is how theoreticians like to think. You generate many trajectories. You just start with particles, for example, in equilibrium, and then you generate many trajectories, and then you just need to look at two times. It doesn't matter where, because this process after a long time is becoming stationary. And then you just look at time t plus tau Vt over an ensemble. So this average is over an ensemble. And this correlation function will be the same, when it will be the same in the long time limit, which means that you for example, when you prepared your system in equilibrium, or this guy t is long that you forgot the initial condition. Okay? So this is two ways to measure this type of correlation function. And this correlation function, I just denote it as correlation. In our case, it's a velocity correlation function. So I write it as cor tau. It's simply cor tau is shorter than this. Is equal to this, k Boltzmann t exponential minus gamma tau. The way you get it, a little bit hand waving, I admit, is you have Vt average is equal V0 e to the minus gamma t. Now what we are doing here actually, if you have a stationary process that does not depend on anything, what you're saying is like this. Let us look at V0, Vt, average, and now average also over the initial condition. And what I mean by initial condition, I'm averaging over a thermal state, over the Maxwell distribution. Why? Because think about the process here. You see, I take it here, and then I take it here, and then I take it here. What is the initial velocity here? And here, each time it's something else, but each time it's equilibrium. So I just need to average over Maxwell, and that gives you V0 squared average, and that is equal to k Boltzmann t over m e to the minus gamma tau. This will be, okay, then this will be tau. And again, this we use the fact that this process is stationary. It makes sense. It just says what is the correlation time? It's 1 over gamma. In principle, you can derive this from this equation. Why? Because what you do is you need to use a Markovian property of the probability density, and that is the probability to be at some velocity at some t1 it depends on the velocity at time, previous time, and that depends on the initial condition, and then you can average over 2 times and get this result. I'm not deriving this. I want to believe that you intuitively at least understand it, why this also indicates a relaxation on this time scale. This will be important after the break when we will go and see what is the relation now. The next question is, I'll soon give you the solution, but in next class I'm going to ask, what is the relation between D and gamma. And D, remember, is given by the MSD. Up till now I was talking about the velocity. This is the diffusion coefficient, which you can easily measure. You just look at the particle, you look at its motion in space, and then you average over many trajectories, and then you find x squared 2dt. That you know already from the diffusion equation from random walks. Random walks give an interpretation of this. What did Einstein tell you? That D is equal delta x squared over 2 tau, where tau was the time between jumps in the random walk, and delta x squared was the variance of the size of the jumps. But we don't have any delta x squared, we don't have any tau squared. What we have is gamma. So we want to relate gamma and D. And that would be cool, because if we can relate these two guys, then if I know gamma, I know D. Or if I know D, I know gamma. And if I know D, I know the viscosity, etc. And that is really the great idea of Einstein. Just for completeness, let me write down the solution of this equation. You can easily derive it. Or just check that what I write is correct. So the solution of the Fokker-Planck equation is like this. PV and T is equal 2 pi k Boltzmann T over M 1 minus E 2 gamma tau, all this to the power minus half. This is like a normalization constant, but this normalization constant depends on time. Exponential M, the mass, V minus V0 e to the minus gamma t, this squared, divided by 2 k Boltzmann t 1 minus e to the minus gamma t. This is the solution. And you can easily see what happens at very short times and what happens at very long times. So at very short times, you see this exponential is roughly 1 minus gamma t. So at short times, 1 minus gamma t e to the minus gamma t is gamma t. This is when gamma t is much smaller than 1. This gamma t more or less is going to be e to the 0 to leading order. So what do you have here? You have m v minus v squared squared divided by something very, very small. What is this in the limit where t goes to 0? Together with this normalization, unless v is equal to v0, this function is going to be e to something very big. So this is going to simply go to a delta function, as you can see. So hence, PV and T, you can check that it goes to what you expect. And of course, in the opposite limit, gamma t much greater than 1, then what happens then, you see the velocity, the initial condition, this is the initial condition, decays. So at large time, this is e to some big number, this is very small. This also is very small. So everything here becomes time independent, and also this guy is small. So as you expect, PV of t, it's not surprising, it goes to the Maxwell distribution. But essentially, for any time t, this velocity has a Gaussian distribution. What do I mean by Gaussian? It's a shifted Gaussian. You see, because of this square here. So the Gaussianity of this process is maintained. The random variable v in this theory is always Gaussian, but it's not a Gaussian on 0 like you had in the diffusion equation. You started at x equals 0. You have a Gaussian that is moving. So the description is something like this. Let's say this is v0. You start like this. And this is velocity 0. You end at something like this. So at the beginning you are very narrow because you know your initial condition. This is t equals 0. This is t to infinity. And then as time goes by, at very short times, by the way, you will not see this gamma at all. Not exactly you will not see the gamma, but at the beginning you will not see the drift. So at the beginning it will be something like a Gaussian around this guy, and then this Gaussian is kind of moving into this direction and becoming fatter, and eventually you go to this equilibrium shape. Okay, so now let's go for a 10-minute break, and then if there's no questions, and then we will continue with Einstein's work and try to relate friction and d. So now we want to derive something called the Einstein relation. To confuse you, actually there are 3 Einstein relations. This is one of them. They're all slightly related. But I'll just call it the Einstein relation. So in many experiments, we actually don't really see the velocity, or we don't measure the velocity. We just look at the position of the particle in space. It's doing Brownian motion. So we want to have information on the diffusion constant. So remember, I said this before, but remember, in the long time limit, the MSD of the particle is given by this transport coefficient d, which is a measurable quantity. You just measure many trajectories. You can measure the Gaussian propagator of the position, and you can calculate this. But what is this d? Or, well, we will not really say what is d because that's too difficult for us, but we will relate, that's why it's called a relation, between d and gamma. That's the idea. And how do we do this? This is very easy. Well, now it's very easy, but we needed Einstein to tell us. This is simply because the position of the particle, by definition, is the integral over the velocity. This velocity now is the stochastic velocity. It's very complicated. It was this very wiggly curve I showed you before. But by definition, x is the integral over the velocity. It just means that we start the particle at time equals 0 at position that we call 0. So if I want x squared, what do I need to do? I need to say what is x squared at time t. Of course, it's some random function. So this integral is a bit different than what you are used to maybe. Because usually you are used to a function, an integral over a function which is deterministic, some given function. But this velocity is totally random. We don't know this velocity actually. Some random velocity. But still, by averaging, we can do this integral. This is simply integral. This is equal integral from 0 to t vt1 dt1. That's x of t. You see the integral is up to t times the integral of vt2 dt2 integral up to time t. Now, the average is over the paths of the velocity. Now I can write it a little bit different. I can write it integral from 0 to t1, integral from 0 to t2, dt2, times vt1 times vt2, average. All I did now is put the average inside. But now you see what is happening here. What is this guy? This is the velocity correlation function. So just before the end of the class, I said if you have a velocity at some time t1, it's correlated with the velocity time t2, and the correlation time is roughly 1 over gamma. We know this function because we just developed a theory for it. So now, great. We can plug this function here inside and then do the integrals. And you practically see what is going on. This function is decaying on a scale of 1 over gamma. So when you integrate out, you'll get the MSD, which depends on this gamma, which is the Stokes law. And that will relate between gamma, which is friction, and d, which is fluctuation in space. So let's do this. First of all, I have two integrals. But it's very easy to understand. We assume now that the process is stationary. And this is always valid in the very long time limit, within the model, I mean. So this velocity correlation function, vt1, vt2, is k Boltzmann t. This we showed in previous class, I mean, just before the break. Exponential minus gamma t1 minus t2 absolute value. We go from the biggest one to the, if t1 is bigger than t2, then this is t1 minus t2. But if t2 is bigger, then it's the opposite, of course. So that's why I have an absolute value here. It's because I have the velocity trajectory. If I have t1 and t2, there is some correlation, but I can switch the labels, of course. So t2 is t1. That's why I have this absolute value here. Now, I can do this integral. You see here I have integral from 0 to t1. If you want, this is t1, this is t2, then this is t, and this is t. So I'm doing an integration in 2 dimensions in a box. From 0 to t and from 0 to, this is a mistake. This is t. I'm doing it in a box. But instead of doing that, I can do it in half a box on a triangle, because I can decide, just let's call one of them bigger than the other, and then I'll have double the amount. So this is equal to 2 integral from 0 to t dt1 integral from 0 to t1 dt2 times the velocity correlation function. So here what I did is, you see in this integral t2 is less than t1. Of course I have the same expression when I switch, but they are the same thing, so I have here this factor of 2. So t2 is less than t1, so this is equal to 2 integral from 0 to t dt1. And now I'm just going to copy the expression for the velocity correlation function. So I assume I start from equilibrium. So again, trajectory is with some v0, but v0 itself is drawn from the Maxwell distribution with mass m. So this guy is simply v squared average. And here I have exponential minus gamma t1 minus t2. And I'm using here the fact that t1 is bigger than t2, and then I don't need the absolute value. Well, this is a simple integral, even I can do it. So what you do is, of course, let us switch from t to new variables. So t1 minus t2, let's call it tau. And then I have t1 is going to be equal to t1. If you want to, you have here a t1 tilde. The point is that the Jacobian here is 1. When you do the transformation, the Jacobian is 1 because these are simple linear transformations. So the MSD averaged is equal to integral from 0. We can take out this k Boltzmann t over m. This is which has units of velocity, of course. Integral from 0 to t, dt1, this nothing has changed. This integral, nothing has changed, and now I'm changing the other integral. And when you think about it, you see tau is t1 minus t2, and the biggest one you can have is when t2 is equal, here is a mistake, this is 2, when t1 is t2, so you have an integral from 0 till t1. So again, when t2 is 0, tau is tau1, this is this upper limit. When t2 is t1, then you start at 0. So this is d tau e to the exponential minus gamma tau. Now this integral is simple. This is 2 k Boltzmann t over m, integral over dt1, integral over from 0 to t. Then you have this integral, and this integral is simply 1 minus e minus tau over gamma. I just do the integration, you get 1 over gamma. And then I plug in the initial, the two limits. So the 0 gives me 1, and this is t1. Good. Now I have another integral. So when I take the first integral, you see it's integral over 1. So this is equal, the first integral is 2 k Boltzmann t, temperature over m, over gamma, times measurement time t. This, forget about this one. So this is because if you have here a constant, then of course integration over t gives you just t. And the second integral is, with this minus time, k Boltzmann t over m, gamma, this one. Then you need to integrate again over an exponential. Integration over exponential gives you, again, 1, to give you again 1 minus e to the minus gamma with another gamma inside. So you will get here 1 minus e to the minus gamma t over gamma. So to summarize, here it is. Yeah. What do I get? I get x squared equal to 2 k Boltzmann t over m gamma times t minus 1 e to the minus gamma t divided by gamma. This is the final solution. Now, you see that gamma, 1 over gamma has units of time, and unit-wise we are finite. Most important conclusion here is the following. We know from measurements, that's our definition of what is d. So the Einstein relation is just saying that in the long time limit, t gamma t, greater than 1, we can identify what is x squared. x squared in the long time limit. So this equality, we see here that this equality that we had for random walk theory, this is the random walk theory, jump left, right, diffusion equation. We see that this is actually not exactly correct. It's correct in the long time limit. Why? Because you have this friction. So at very short times when gamma t is of order 1, this law is not correct. But if you wait long enough, then you see this term is correct, and then the main conclusion is that d is equal to k Boltzmann t over m gamma without the 2, because this guy also has the 2. This is a very important equation in physics because it relates between diffusion, and diffusion we call fluctuation. So fluctuations are what we are studying here. That's the new physics in 1905. Here we have gamma, that is called dissipation. Stokes' law describes how fast you lose your initial velocity, that's dissipation, or you want hydrodynamics. And of course, this k Boltzmann t is thermal equilibrium. So you have here a relation between equilibrium statistical physics, dissipation described by Stokes' law, and the fluctuations describing the spreading of the particle in space. Especially now we understand, if I write down this equation, which is, remember this equation was derived by Fick before Einstein, d second derivative with respect to exp, this is the diffusion equation. Now I know what's this diffusion equation. What I need to do, according to Einstein, I need to measure the viscosity. I need to measure the size of the particle. Then I know what is gamma. By the way, this dissipation constant depends itself on temperature. It's not that the diffusion is linear in temperature, because this is a complicated function of temperature. So because when you change temperature, you change viscosity. But in principle, you measure viscosity at a given temperature, you know gamma, and then you are done. You know the diffusion, and that's a nice thing because you just need to know the radius of the particle, its mass, the viscosity of the fluid, and you know how fast it spreads. That is physics. While here, in the original equation of Fick, this was just some phenomenological thing that you put in. Of course, you can be smart and you can say, wait, but what is this gamma? We don't know what's gamma. So this is why this theory is not a microscopical theory. It's just a relation. You relate one thing to the other. You relate gamma to d. On the other hand, you can gain from this equation, you can gain some more information. You can go, let's see what happens at very short times. So at short times, what do you get? You see at short times the deviation from predictions of, let's say, Gauss, central limit theorem, because x squared at short times, I just linearize this. So this is e to the minus 1 minus gamma t. So what happens here? Let's do it. You have t 1 e to the minus gamma t divided by gamma. So this guy is t minus 1. Then I expand it in this thing, and it's 1 minus gamma t. And if I stop here, what will happen? Everything will cancel, because 1 will cancel with 1, and this gamma t, when I divide by gamma, will cancel this t. So I need to do actually the expansion up to second order. That's the expansion of the exponential. And then I get here, of course there are more terms, and you're welcome to find corrections if you want. But all this guy is equal to, you see minus and minus, then you have here gamma t squared over 2. And that's nice. Why? Because then x squared from here is equal to 2 k Boltzmann t divided by m gamma times, let's write it, gamma t squared over 2. What's nice about this, you see the gamma is cancelled. And the 2 is also cancelled. And then you get k Boltzmann t divided by m times t squared. So at very short times, you're not doing diffusion at all. This motion is called ballistic motion. There's no diffusion on short times. Why not? It's very simple to understand, actually. Initially, on average, your velocity is k Boltzmann t divided by m. So v squared in equilibrium is k Boltzmann t over m. At short times, you don't feel the dissipation. This you know. You go to the beach, you push your something in the water. At very short times, your velocity, your initial velocity is the same as the whatever you started with. So here is k Boltzmann t over m. This is the initial velocity. And from here, you understand that x squared at short times should behave like k Boltzmann t, which is your velocity, times t squared. Just from units point of view, this is obviously correct. So what is happening, if you go back to this equation, is that at short times you are ballistic. You go like t to the power 2. At long times you go linearly with time. And the transition time is 1 over gamma. So the MSD looks something like x squared versus time. At beginning it starts quadratically, like t squared, like a parabola. And then eventually you are linear, so it's t squared. And what is this time scale? This is 1 over gamma. If you are capable of measuring these short times, then you can see this. If you don't measure in these short times, you don't see this. Many experiments, the gamma is so big that you don't see this short time behavior. Then you will call this dynamics overdamped. The friction is gigantic, and then you'll only see this line. Okay, so now we want to make a slight detour from the fokker-Planck equation. The problem is, I told you here that there is a correlation function, and I showed that the correlation function decays exponentially. But in general, this is not correct. That means if you take different particles in different mediums, sometimes it will decay exponentially. For example, a micro bead in water, everything is correct. But people performed experiments after this and saw that the velocity correlation function in a complicated medium can be much more complicated. Maybe it will be a sum of 2 exponentials. Maybe it will be an exponential, and then you have some oscillations. So correlation functions in generality have certain properties. First of all, they decay when the process is stationary, I mean. But they don't have to obey this simple Markovian limit. Remember, what was my assumption? My assumption was that you had a very big sphere colliding with many small guys around it. And then you lost your memory quickly. But if you look, for example, molecules of the same size, they also have a velocity. They are colliding in a complicated way, and they have some velocity correlation function, which this theory has nothing to do with it. So people, after Einstein found this relation, wanted to find a more general relation between friction and diffusivity. And this is what we're going to do, and that is called Green-Kuber relation. It's a very useful equation in all condensed matter. Much of condensed matter is based on it. So you can look at this like this. Let's say you are you want to do a phenomenological theory. You have some data on your velocity, and you want to predict your so this is my correlation function. It's a function of tau only. This is already meaning that this process is stationary. So you have this velocity as a function of time. It fluctuates in a complicated way. This is your data as a function of time. You look at 2 time points, different tau. You do a moving average. That is a time average. The velocity correlation function depends only on this tau. Then you make tau bigger, and then you plot it as a function of time. That is the correlation function as a function of time is simply equal to Vt plus tau Vt. Average is and it's independent of t. Because this time choice is very long, and when I mean stationarity, I mean that the system is time translation invariant. What does it mean, time translation invariant here? You see the velocity here and here are not the same, but the correlation function, if you measure here, the velocity correlation function here or here or here or here or whatever, is independent of tau. And in our previous example, this was equal k Boltzmann t over m e to the minus gamma tau. So this was in example 1. This describes a massive Brownian particle surrounded by small particles. But in general, you will have here maybe something like a sum of exponentials. So the correlation function can be many, many things. A common thing, however, will be that in thermal equilibrium, this is a generality. It's always V squared is always equal k Boltzmann t over m, right? Because this is Maxwell. So the correlation function, if you want, I can divide it by k Boltzmann t over m, starts at 1. And then you can have something as complicated. This is not random. You can have something like that. For example, oscillating. You can have something simple, exponential. You can have something always positive but decaying. The general property of these functions is the decay. Why? If you look at 2 times, velocity, and the time is very different, then, okay, the velocity here is not correlated with the velocity there. That is the assumption that it decays. Eventually, this correlation function has to go to 0. We will soon see how fast it has to go to 0. Not if it goes too slowly to 0, like a log power law, then the diffusion constant might not be defined. But we assume a generic behavior when we have some correlation function which is only depending on tau, which means a stationary process. So these are very general conditions. This happens everywhere. Not everywhere, but to put it differently, after Einstein's theory in 1905 till roughly 1960, everyone was working on this, and condensed matter people continue working like this because everything is stationary, they assume it, while other groups of people go to non-stationary processes which are related to anomalous diffusion, where the diffusion constant actually depends on time. But that's a different story. So let us just assume this, that's what Green and Kubo did. And then the exercise now is kind of similar to what we had before. Again, we want to know what is the relation between this correlation function and the diffusion. So the idea here is the following. I'm not doing all the steps because some of the steps were just done. So I have an integration over T1, I have integration over T2, then I replace it with integration of T1 and tau, okay? This I did exactly like before. I don't want to do it again. And then you have, generally speaking, without assuming a specific form of the correlation function, dt1, integral over T1. So this 2 is because before I had integration T1, T2, and now I divide it into 2 parts, T1 and tau. like before, but now I have correlation function of tau. And it's the velocity correlation function. So before we had here an exponential function, now we have a general function. That's all. So now we have to think a little bit about this correlation function as a function of time. Of course, I'm thinking about a wide family of correlation functions. This function, I'm going to assume, kind of decays to 0. And there is some t star that I'm going to say, after this t star, hell, this function is 0. This t star is just a theoretical thing I put in by hand. For example, we have here exponential minus gamma t. So 1 over gamma is the time. 1 million times 1 over gamma, it's exponential to 1 million minus 1 million. That's 0. It's really 0. I mean, mathematicians don't understand, but it's 0. So we have here some cutoff where this function is going to be more or less equal to 0. Again, in the previous example, so it means that there is some typical time scale. In the previous example, it was 1 over gamma, but you know, here I have some time scale, maybe 2 time scales. There's sum of exponentials, or sum of exponential times a cosine function. It doesn't matter. Some time scale, which is a typical time scale of relaxation, and we assume it's finite. If there is no typical time scale, then you will get weird things like anomalous diffusion. But in this process, there is a time scale, and we assume that this time scale is 0, and this is something specific for the correlation function. I don't know what it is, but okay, there exists some length, I guess. So then I write it like this. I write this guy as 2 integral from 0 to t star dt1 integral from 0 to t1 correlation function tau d tau plus integral from t star till the measurement time dt1 integral from 0 till t1 correlation function tau d tau. Now what we are going to do is we're going to assume that t is much, much bigger than t star. So imagine that this t0 is a picosecond, relaxation on the time scale of picosecond, 100 picosecond, this function is 0, but we measure the MSD on seconds. So 100 picoseconds is much, much less than when we measure on time scales of 5 seconds or whatever. You understand the big time differences. So the fact that this guy is big compared to this doesn't mean that the measurement time is even bigger. And then when you understand this, so this is an integral, again in my example, up to let's say 20 picosecond, the relaxation is 1 picosecond. This is a relaxation over seconds. This guy is big, and this guy is small. We're going to throw that guy away. Now, why did I do this? What did I get here? You see T1 here.
How is that big if all tau is almost 0?
Where? This one?
Yes.
I'm just saying that this guy is bigger than this guy.
Yeah, but core is going to 0.
Core is going to 0. Yeah, but it's an integral from 0 to T1. From 0. And let me finish, then I think you'll understand. T1 is bigger than T star. So this integral that we have here over T1, called T1, called tau, d tau, T1 is bigger than T star. Then this guy I can approximate from integral from 0 to infinity. Because we said that after t star, this correlation function is 0, so I might as well integrate till infinity, assuming this integral exists. So what I do here is I replace this object here, because all the t1s are very big, with this object, integral from 0 to infinity. Then I have to do this integral. What is this integral? That's easy. It's t minus t star, because now this guy is independent of t1 anymore. So the integral dt1 from t star till t is equal to simply t minus t star, but t, as I mentioned in the example before, these are seconds, these are picoseconds, this is more or less t. Is this now clear? You have a question? Well, you had a question before, no? Ah, sorry. Because you see now here, the left one is smaller because of the integral from 0 to t star, while here you have t star to t infinity. So you see here what happens, this guy is now proportional to t. So let me just write it down. So x squared is equal to 2t integral from 0 to infinity correlation function tau d tau. Just to answer your question, I hope you agree that this integral here, if you do the same thing, even if you do the same thing, this integral will give you, assuming, let's say, this is bounded, this will give you integral up to t star. And then you will have here a t star. But t star, I'm saying again and again, is much smaller than t. T is the really long time limit. So let's go back to this equation. And you can easily plug in here what we had in the previous example. What was the previous example? So example is that x squared is equal to k Boltzmann t over m. That's the velocity correlation function, integral from 0 to infinity, e to the minus gamma tau d tau times t, this t. When I do this simple integral now, this is equal to 2k Boltzmann t over m divided by gamma, this I get from the integral, times t. And this is exactly the Einstein relation. So there's nothing new here. I just did the same thing as before. I assumed a very specific correlation function. This is Einstein's theory. But now, this is the Green-Kubo theory. Now what I have here is something more general. I have an interpretation. What is the diffusion? That's all. I have an interpretation. What is the diffusion constant? I understand it. Of course, you can claim I didn't understand much, because what is this correlation function? I didn't say what is this correlation function, but I say that any measurement of diffusion constant is actually, what you are actually doing is you're taking your velocity correlation function and you're integrating all over it, and then you get the diffusion constant. Because what is this guy? You see x squared is 2 times dt, so what is the diffusion constant? This is the Green-Kubo relation. D is equal to integral from 0 to infinity, the correlation function tau d tau. Just to make sense, or when you read it again, the correlation function from unit points of view is velocity squared. If I multiply it by time, I get x squared over time, and that is, of course, the correct units of d. So unit-wise, the velocity correlation function, you take it and then you can compute it. Of course, why is this important? In, let's say, numerical simulations, many people do a lot of numerical simulations. Instead of measuring x squared, you see why it's beautiful is the following. we said that the correlation function, it can be a complicated function. So you put let's say in your simulation, you put some particle in a simulation, and you can measure your velocity correlation function. You measure it, and it looks something crazy maybe, but you assume or you hope, it goes to 0, and then you assume later on it's 0. So you have this correlation function, and this can be on time scales, in some cases, not all cases, very short time scales. So you measure it in a computer simulation, you have the velocity correlation function, and then all you need to do, you need to take this integral, assuming that you can stretch your simulation from here till infinity. This is an assumption, but if you see something which is 0 for some time scales, you believe it will continue. You do this integral, and you know the diffusion, which is what you measure from the MSD. So many people, when they want to calculate the diffusion constant, they will actually measure, or by simulation or by experiment, they measure the velocity correlation function, and then they have information on the macroscopical data on the longer time scale. Of course, this is very different than a random walk picture, because what did we say in a random walk picture? Again, I said it before, but let's say it again. This is, in the random walk picture, this is the diffusion constant, the size of the variance of the jump and tau. This guy is an Einstein relation. This is a Green-Kubo relation, but it's actually like an Einstein relation. It's just a slight generalization of the Einstein relation we had previously. So there are many relations between different things, and you need to understand them to get the history. We will soon derive the third Einstein relation. So now we want to discuss in slightly more generality the fokker-Planck equation. Do you have questions on this? Is this more or less clear? Okay. So up to now we discussed the fokker-Planck equation, but it was a special one which assumed, for example, linearity of the friction. But Fokker-Planck equations are applied to really a wide variety of systems, from physics, chemistry, stock markets, economy. These are very general processes which are continuous. They study a lot of mathematics. So in generality, what is the Fokker-Planck equation? It's an equation. I'll now discuss the Fokker-Planck equation when you have only one variable. I call it, before it was velocity. In diffusion equation, it was position x. That was diffusion equation. Diffusion equation is a special case of the Fokker-Planck equation. But now we're just going to call it y. In principle, in real systems, you have a higher dimensional Fokker-Planck. So this is a one-dimensional Fokker-Planck, but the generalization are easy. So the Fokker-Planck equation in one dimension generally looks like py of t minus d over dy a y. So before, what I did is I said this a is, this was the drift, right? We added linearly with y. Before this was the velocity. So that gives you the linear friction. But now it's some function, some general function, plus half second derivative of y. And now I have by, all this is acting on p of y and t. In this equation, we have two terms. This term we call drift. Drift term. It can be very complicated drift. It's locally a drift, but if this function is complicated, it will eventually describe, for example, an external force field acting on the particle in position space, etc. This we call diffusion. But it's not like the diffusion you had before, because now this function depends on y in principle. So what does it describe? Think about diffusion constant. We showed that diffusion constant depends on gamma, right? But let's say that the gamma, the viscosity, is changing in your system. For example, you have a system, one part of it is water, the other part of it is honey. The viscosity here is different than here. So your diffusion constant will be changing in time. Or in more practically, you have the cell environment, and one part of the cell you have very high density of objects that makes the viscosity higher because the particle cannot move, and in another part of the cell it's more fluid-like, it's more gas-like, or whatever, the diffusion constant is small. So in principle, both forces and diffusion fields can be varying in space in a very complicated way. And then we must treat these things in general. Only thing we assume, of course, is that these two functions are real. But this is something trivial. Y is some coordinate. So again, I'll define it. I want to make it a general theory. This is mathematical, some abstract. So we saw some examples. So dt p x and t is equal d. You saw this equation, right? So in this equation, y is x, a is 0, and b is d. Half b is d. This is the diffusion equation. Then we saw another equation for the velocity of the particle, p, v, and t. Plus gamma d over dv, v plus k Boltzmann t over m, d over dv, p, right? And so in this equation, y is the velocity of the particle. It's not the same thing. Sometimes it's position, sometimes it's velocity, and sometimes it can be many, many more things. And in this case, you know, A was, we already showed this in the previous class, A was alpha, gamma, and B over 2 was gamma k Boltzmann t over m. So we are flexible. We have something called y, which is fluctuating. We have some stochastic process. If you want to think about it, we have some general stochastic process where you have y as a function of time, and you have these trajectories. And maybe y, if you want to think about it in space, you have a trajectory, a very complicated trajectory, and maybe the properties here and here are different. So you have these type of trajectories, and then you want to construct these type of equations in a complicated medium in general. What do we know immediately? We know, assuming that py at infinity is 0, by integration by parts, we have that the derivative of y is equal, so this is integration by parts. Like we did before, but slightly more general, I multiply by y, I integrate over y, I take this derivative, this is second derivative, so if I have here a y, I'll have the thing here, I assume that b goes to 0 at large y, and p also even stronger. So I just have this is equal to plus a y average. This sometimes is useful because sometimes you know this from macroscopic law. For example, this is what we did before. This was known from Stokes' law. But let's say you have a different macroscopical measurement. That means that you can do some idealized experiment where the diffusion is negligible. Or you have some theory where you have this thing, then you have y dot equal ay. This is why we call it also a drift. There's no diffusion here. This is like in physics, what is this? If you believe in Aristotle and not in Newton, this is the derivative of, let's say, position is equals to some average force. So this is why we call it drift. So in this description, there will be no, inertia. You have some rule. We can look what is delta y over delta t. I want to explain how, in principle at least, you get this ay and by from trajectories, or what are the meaning in general. So, what is delta y? This is some y minus some y0. So, I have a very complicated trajectories in space. I assume now that the fokker-Planck describes this. I want to interpret these trajectories. I go to some place. I call this place y0. Then I look at some delta t, and then the particle can jump up, left, right, down in 2 dimensions, but we do it now in 1 dimension. And then it comes here, and then sometimes it jumps here, sometimes it jumps up, down, in a stochastic way, because this is my data. And then I average many, many times. And then in principle, I hope you agree that I can measure what is delta y over delta t. Just look at the particle, oh, it's here, this is y0. You look at delta t, oh, it's here, particle 1. It again here, now it's here, there. You measure delta y. So you average this, and then you get, this will be equal to what? A of y0, because delta t here is small. So in the limit, this is simply a y0. So this is how, in principle, you can measure, if you have no idea about the system, what is this function a of y. You go to different y's. If you are lucky that your particle is in that position, it makes these jumps in a random way. And then you measure some small delta t, you look at the displacement, delta y, divided by delta t, and from this equation, you get this equation in the limit delta t to 0, and then you have this function a of y0. I hope everyone understands why this is a of y0, because this is a of y, but y did not change much. Delta y is also small, so a of y goes to a of y0. So we know how to, in principle, infer from data what is this function. It's this force. We call it a force. Similarly, I can interpret what is this b of y. And b of y is delta y squared over 2 delta t. Again, in the limit delta t is going to 0. So you are in some position in space here, close to y0. The particle, as I said before, jumps left, right, up, down. You average over not delta y. So delta y, if you have a drift somewhere, will give you some delta y. But even without a drift, you have delta y squared. And then when you divide it by delta t, this is the physical meaning of by0. Meaning, again, that from a set of data, you can infer from trajectories what is this by0. What is this generalized diffusion constant? This actually is not trivial, because you see you have the square divided by delta t. Delta y is a fluctuation, but it scales with delta t, not with delta t squared. But this limit exists in diffusive process. That's the whole point of this. So, and you know this. This equation is not totally new. You know this, for example, from the diffusion equation. So this is actually a small generalization of Einstein's relation. Why do I say this? You saw this already. So for example, a random walk. I want to approximate it with this diffusion equation. So what is delta? So let's do it like this. We already said it, but let's say it again. Here I have a lattice spacing which I call A. Then I make a jump every delta t. The probability half to jump left, probability half to jump right. In this case, delta y is just the position of the particle. And what is delta y squared over delta t? I called this before delta x squared, but this is simply a squared over delta t. So a squared is the size of the lattice. A is the lattice distance. Delta t is the time between jumps. And you take a squared in such a way, that's the issue here, that a is small, delta t is small. This gives you some constant that we called before d over 2. Here I have 2, d times 2. This is d times 2. And of course, in this random walk, delta y, delta t, average is obviously equal to 0 because I jump here left and right with equal probabilities. So this delta y, which I identify with the position x, is simply equal to 0. And then, as you know, as I said it already a million times, dp x and t is simply d second derivative of p. So this equation is simply saying maybe d is changing in space or in y space, so it can in principle depend where you started from. And similarly for the drift, which was 0 here, now we have some drift, two functions. So now let us try and use it in two steps, physical steps, to get the third and final Einstein relation, which is maybe the most important one. This equation, by the way, I did not derive, but you simply multiply the fokker-Planck equation by delta y, you integrate, and you get it. But it's a simple exercise. I'm not going to do it. So let us assume we have Brownian motion plus some external force. So I have a box and I have a Brownian particle, but it has a charge. So let us assume it has a charge E. And I apply an electric field in the x direction. So this is an electric field in the x direction. So the force, I can write it without vectors because it's in one dimension, is the charge times the electric field. The charge is the charge of the particle. It can change. I mean, it's not the charge of an electron. But we can also do this for the electron more or less. Now, what is we are now going to assume what is the velocity of the particle. So we are going to look. According to this prescription we had here before, we have to look at we are interested in position. What is the position? What is the equation for P, X, and T? So in this case, my y is x, position of the particle. And I'm also not going to look at it at very short time scales where the velocity is important. I'm going to look at it like I look in the diffusion equation in a slightly longer time scales where we have diffusion. So we have a diffusion constant, and we have also some drift. So what is the position of the particle? X as a function of time, we expect it to go in the direction of the force, linear in the force. So this is something called linear theory, linear response theory. So you have a force. Now the idea is you have a force, but you have a friction. And that's why even though you have a force, this doesn't go like t squared, because the friction stops it. And then it's simply linear in time, you have some increase. What is this force? So we know that if you add, according to Stokes, let us look at the averages only. This is the general force. It's consisting of the friction force. This is Stokes' law. We know gamma, same as before. But in addition, we have this force. This is, I want to write V dot, like before. And this is F divided by M. This F now is not the friction force, but the force due to the electric field. This is simply Newton's equation, but I add here both friction and the external force. I divide it by M, and then I get this equation. And the force is assumed position independent. So now at long time, I have delta V. At long time, this is 0. Simply, very simple. You take a ball in a glycerin. You throw it from upstairs. You know what will happen. You have mg, that's the force. After some time, it goes to a constant velocity. Everyone knows that that's daily life, and this is the constant velocity. So I just write it delta V over t is equal F over m divided by gamma. So if you want to think about F not as an electric force, you drop a particle. At the beginning, it has some acceleration if you start from 0, but then you have mg going down, and then you have a friction that stops it, and then, excuse me, this is not delta V, this is delta x. Because this is V, sorry, V is delta x over delta t. So I just said delta x over t is F equal ma. And this is the velocity. But now, essentially, we are done, because we know that now we assume, okay, there are several more assumptions. The same assumptions that we had before, that there is no memory in the bath, that the collisions are frequent. So now let us write again a phenomenological equation describing this guy. So we have now the derivative with respect to time, px and t. This is equal, first of all, I assume that there is a diffusion. That is this term, essentially. B, I'm assuming that there's no space dependence. So the medium here and there and everywhere, everything is the same diffusion constant. And then I need to add this delta y. It was now, it's not on the blackboard anymore, but I need to subtract the drift. But the drift is independent of x. Again, x is what we had before y. So this is simply F over m gamma d over dx p. So this describes diffusion, and this describes drift. But first of all, we know already that D and gamma are related. They're not independent. So we can use that, or we can again prove this, what we proved before, with this. So before I found a relation between D and gamma, right? How did I do it? I first wrote an equation for the velocity. I then found the velocity correlation function. Then I integrated, got x squared. Now I can do something very different. Let's say I don't know about this relation. I can say I have D and gamma. But let's say I have here a wall. So the force is acting like this, and I'm pushing it like that. So then I know that P equilibrium of x is some normalization I don't care about. Exponential f times x k Boltzmann t. Here, this is x equals 0, let's say, so this is negative. You know this law. This is simply Boltzmann's law. This is simply f times x is this thing is the potential minus the potential. So when x is minus infinity, the probability of finding the particle is 0. So all the particles are in the vicinity of the wall. This is, of course, what you know from gravity. If we are here on Earth, when you go upstairs, the concentration is going down exponentially. This is it's called the barometric formula when F is equal mg. Now I can plug this in here, and similar to before, I have that P equilibrium is determined by this equation. I can take 1 dx outside, then I have d over dx minus f over m gamma. Here I have this expression. This is equal 0 again, because this is equilibrium. This is after the system reached an equilibrium. And now when I take the derivative here, I get f divided by k Boltzmann t. So I get d f divided by k Boltzmann t equal f m gamma. So here I get d k Boltzmann t divided by m gamma. See, this is what we had before, right? The same thing, but very different argumentation, because here I had only position, while here, before I had velocity. But the trick is the same trick, because you see this equation that I wrote here, what is it? It's the long time limit solution. So you go to the long time, you assume you are in thermal equilibrium, and then you find a relation between this gamma and this d. Or you could simply use this relation and put it in here, as you wish. So this was just a second way to derive Einstein's relation without using velocities at all. So you start, why is this important? Because it shows you that maybe this Einstein relation and Einstein trick is very useful in general. It's not only for velocities, it's for positions and equilibrium in general, this trick. And indeed, the theory is far more general than these simple examples. כן, עוד שעה. היום יש לי שעון. So now we can say something about conductivity, because we know that the velocity, what is the velocity? We started with the velocity, so we have it already. We said already that this velocity is F equal divided by m gamma. F is the external force, proportional to the electric field, if you want, times the charge or whatever is the force. The force does not depend on space, but this is what it is. In condensed matter physics, what you do is you say this is equal to something called mu times F. Mu is called the mobility. Why is this important in condensed matter physics? Because what they measure there usually is the currents. And the currents are measured, and then they measure some friction. But what is this law? This is essentially Ohm's law. Because if F is related to the delta V, this is essentially the resistivity, one of the resistivity. So when you measure the current or you measure the average velocity, you get this mobility, and its linear response. Within linear response, what do I mean by linear response? Is that mu is independent of F. That means that in practice the forces must be weak, but in condensed matter this is always the case. Not always, but most practical forces, the external force is weak enough. So you know it from Ohm's law. The resistivity doesn't depend on the voltage. It's some constant related to the material. So from here we get that the mobility that you measure is 1 over m gamma. So you are relating the friction. This is saying, okay, mobility is something to do with friction. Maybe surprising, or I don't think it is surprising, but what is really surprising is that we know that D, let's copy it from there, is equal K Boltzmann T divided by m gamma. So now it's very easy to understand that mu and D are related. And what is this? This is a famous Einstein relation. It's mu over K Boltzmann T. And this is a super important equation because it shows that the mobility, where all the transistors you use, all the laptops essentially are based on some electronic currents. So if it's an electron, the mobility of the electron is equal to the diffusivity divided by K Boltzmann T within Einstein's theory of transport now. This is transport. Why is it transport? Because now you have a force field, so you are moving something from one place to the other. This is not diffusion. Mobility is not diffusion. Mobility is an average quantity that you measure. So this, if you want, is condensed matter physics or Ohm's law, whatever. This is fluctuations. And this is, of course, thermal physics in equilibrium. So Einstein is saying, okay, if you know the diffusion of the particle, you know its mobility. It's a bit weird. I mean, it's very deep, actually. But what he's saying is the following. You can do several types of experiments, and they are all related to one another. Just to summarize the whole ideas. I can take a particle in my liquid, measure V average, let's say it decays exponentially, and then I can measure this and get gamma. So this is a relaxation, this is called a relaxation experiment. This is T. I'm in the swimming pool, I throw something, initial velocity V0, it decays with time, you measure this gamma. If I know this gamma, and I know the temperature, you can get from here both the mobility, see here, and d. But what is the mobility? The mobility is a very different experiment where you have a force acting on the system. And then you have your velocity, as we wrote before, is equal minus mu f. This is an experiment without any force, just a relaxation. So by a relaxation experiment, dissipation experiment, you get both the mobility and the diffusivity. Or you can make this very different. You don't start with some special velocity and you see this decay. You do something else. You have your particle. You just let it diffuse. And you measure d. If I measure d, then from here, I know how fast it relaxes. And then when I add a force, plus some force, I know how fast it moves. I get the mobility. All are related. These are the Einstein relation, these are the powers. In particular, let's say you are doing a theory of condensed matter physics, and you want to calculate the mobility. Why? Because you want to flow some current in some system, and you want to predict what's the mobility. What do you actually do in your theory usually? You calculate the diffusion constant. Why is that much easier? Because there's no force. So you take your system, let's say you have some computer simulation, you have all the interactions inside, for example, if you can do that. You just follow the particle and you measure its diffusion constant. You didn't add the force from outside. And once you measure the diffusion constant, you can predict the mobility. So again, the gain here is that when you do this simulation, you don't need to apply the force. Which force anyway? I mean, weak, small. So if you didn't know the theory, what would you do? You would apply force 1, then a force 2, then force 3. You would look for all the forces. But here we say that if the system is with a linear response, do the experiment or do the measurement without any force, get d, and from d you get mu. And from mu you get the resistivity, and you're done. Of course, getting d can be very complicated. I'm not saying that this is easy. You can measure this, or you can have a theory for this, but then you have many more informations beyond the diffusion equation itself. Now, this relation has its limitations, because this is valid when you have this fokker-planck description, when the decay of the velocity correlation function of everything essentially is exponential. We already said that this d you can calculate more generally with some correlation function by Green-Kuber relation. The same holds for this mobility. In more general case, there will be a relation between the mobility and what? The velocity correlation function in equilibrium. That is called linear response theory, and we will study this next week. In general case, when you don't have this velocity correlation function decaying exponentially, how do you get the mobility? It's not exactly equal to the diffusion constant. You'll see more generally when you have an AC field, it will be related to the velocity correlation function, but in equilibrium. You don't care about out of equilibrium. Out of equilibrium, I mean, when the force is not zero. So you do everything in force 0, and you apply it to what you care about is when the force is not 0. Okay? So this will be next week. So I guess I'll see you then.